Perhaps the most difficult kind of concept in organic chemistry is the idea of especially NMR spectroscopy. Now we're not dealing with reactions anymore, and it's kind of hard to learn at first because you're so used to reactions SN1, SN2, and then all of a sudden you just get into graphs and all this good stuff, right? So with NMR, the first thing I just basic two definitions I just want to point out to you when looking at graphs, so we could kind of practice it and kind of come up with these structural formulas. So the integration, and usually it's given to you. The organic professors are not that, I don't believe, across, well, nationwide in America and perhaps in Europe or wherever you're at. I don't think they'll make you calculate integration because the idea of organic chemistry is not calculations. That leave that stuff for general chemistry. So integration is usually given to you, and it tells you how many protons you have vibrating, right? How many protons you have vibrating, right? And you'll see what I mean once we start doing examples. And then the second most important thing that you need to know is just looking at the graph and the multiplicity, right? Which we kind of explained in a previous video. If you guys want to go ahead and check it out, right? So the multiplicity, right? How many splits are we seeing, right? And the multiplicity essentially tells us how many neighbors. How many neighbors we have. That's what multiplicity tells us. Now, let's jump straight into some examples because these are kind of, it's much easier for me to sit here and say, okay, well, let's do some spectroscopy and kind of tell you guys what to do, but you actually don't see it until you start practicing problems for yourself, and it's kind of really difficult to teach. But my idea here is to give you a concept and just a general thinking of how I look at these problems when I'm trying to solve them. So here we're given the molecular formula C10H14O, right? And we're given the IR spectrum, but also we're given the most powerful tool in spectroscopy, essentially the NMR spectrum. So I'm not going to focus too much on the IR spectrum, but we could kind of use that and kind of come back to a sense, some sort of sensible conclusion. So we're going to leave the IR spectrum and kind of come back to it. This is what I want you guys to focus on, right? So I'm looking at this graph here and I'm asked, well, we're given the molecular formula. Maybe I should write it here. C10H14O. And I'm saying, well, what is going on? How would I tell what's going on? Well, usually how I think of these problems, I'm going to look at my NMR graph, right? Now I see that I have around 7 parts per million, and these are given in parts per million. I see this multiplied here, but it gives me an integration of 4 hydrogens, which means that I have 4 hydrogens there, right? So usually whenever you see some sort of multiplet splitting pattern around 7 going around to 8 parts per million, that's usually associated with a benzene ring. So I'm going to draw my ring. I'm going to draw my ring. I'm going to draw my ring. All right, it's usually associated with a benzene ring. All right, so there's my benzene. Now I have 4 hydrogens vibrating on this molecule. So I'm going to draw 1, 2, 3, 4. Now, if I have 4 hydrogens, this means that this molecule has to be disubstituted. It has to be disubstituted, right? Because there's only 4 hydrogens vibrating, right? The integration is 4, right? So it has to be disubstituted, right? So immediately after I draw my ring, I have 6 carbons taken care of. So I need some way to place, 4 more carbons. Right. Well, now I look here and I see that I have an integration of 1. So I have 1 hydrogen that's vibrating, but it only gives me a split of 1, right? Which means that this hydrogen has to it must have, essentially 0 neighbors. It has to have 0 neighbors, right? And also see a 9 hydrogens kind of vibrating here with only a single split. So if I have 1 hydrogen that's vibrating, look what I'm going to do. I'm going to essentially try an alcohol. So I'm going to put an alcohol on this group here. All right. And it kind of makes sense now because I have 1 hydrogen that's vibrating, which means that it has 0 neighbors, right? Because remember, we said the n+1 rule. If it has 0 neighbors, then we're only going to see one split, because 0 plus 1 is equal to 1. This proton has 0 neighbors. It's bonded to the oxygen. The oxygen is not a proton. So therefore, this is concurrent with what we will see. Now, I have 9 hydrogens here that's vibrating, right? So how I'm going to think of this is that I still have 6 carbons here. So I'm going to draw one out. Now I have 7 carbons, but I have an integration of 9, which means that some way I have 9 hydrogens vibrating with with essentially 0 neighbors. So I'm going to think of this as a tert-butyl group. All right. I have, these hydrogens here, these CH3s here. I have 3 groups of CH3s that's vibrating, which is equivalent to 9 hydrogens. And they have 0 neighbors, right? Because again, look at it. All these CH3s are essentially equivalent, and they have 0 neighbors. They're equivalent, right? The next carbon over, there's no hydrogens. So this is equivalent, right? So let's draw the neutral product. I'm going to just draw with an O because it's easier. And then we have our tert-butyl group here. So this would be the molecular formula of this compound. Now let's take a look at the IR to kind of come to a final conclusion. Well, here we have an OH. Remember, from IR spectroscopy, we know we have an alcohol. So this has to be an alcohol. It has to be an alcohol. And the rest is just pretty much details that we don't really need. We just want to know that this is an alcohol, and we have C10H14O. Well, we have one oxygen, and we have 1, 2, 3, 4. All right, so right now we have 5 hydrogens. All right, and then we have 3 hydrogens here each. So 5 plus 9 plus these 9 hydrogens here, it's actually 14. We have 10 carbons, right? We have 6 here in the benzene ring, and we have 7, 8, 9, 10. So everything matches. Now with these problems, if one thing is incorrect, the whole problem is correct.